for me to introduce Christophe Breuil, and he will give us a series of 4 lectures on the p-adic Langlands program for GL2F, where this F is a local field, but I think the first 2 will start. Okay, and the coefficients, I mean, in the Langlands program are also local fields, but the first 2 lectures will be actually about coefficients in finite characteristics.
Thank you very much. Thank you very much for the invitation to this nice program. So I guess the subject of this talk doesn't lie at the heart of the program. So I prepared 4 talks in a kind of a mostly expository way. Although I hope that some of the experts here will find some food for them. So let me start a general introduction of this p-adic Langlands program for GL2F. Explain very quickly what's the point. So general introduction. So let me start with rho being a representation of the Galois group, a local representation of the Galois group, Galois QP bar over QP, which is 2-dimensional, so with value in GL2E, which is where I'll tell you what E is in a minute. It is a continuous. And in these talks, E will be either a finite extension of QP or a finite extension of FP. Okay, and well, in the past years, there's been lots of work about trying to associate to such kind of representations of Galois representations of GL2 QP over E vector spaces. And so several people have been involved in this, and this cumulated with the work of Colmez, who associated to such a rho. He associated a representation of GL2 QP over an infinite dimensional E vector space. So let me just point out, of course, that the residue characteristic of the coefficient field is the same as the residue characteristic of the group involved in the Galois group, of the field involved in the Galois group. This is, of course, the point of all this stuff. And so this representation, of course, depends, I mean, looks different whether you work in characteristic 0 or in characteristic P. If E is a finite extension of QP, then usually it is denoted by B. I mean, it depends on notations, but this is a Banach space. And this is even a unitary Banach space, p-adic Banach space, of course, over E, together with a continuous action of GL2 QP. And unitary means, in that setting, that there exists an invariant norm. You know, this is a Banach space, so you have several norms which you can choose, which are equivalent. I mean, there's one which such that the norm of G of V is the same thing as norm of V for any G in GL2 QP. There exists an invariant norm. Okay, you can also, so in this setting, there's lots of representations that turns out to occur. There's a sub-representation of B which is almost as good as B. It contains essentially all the information that B contains, but which has a kind of different flavor. It is the subspace of locally analytic vectors. So this is inside B, different from B. This is subspace of locally analytic vectors. That is vectors such that the orbit map viewed as a function on GL2 QP is locally analytic on the p-adic Lie group. Subspace of locally analytic vectors. This kind of representation, Peter Schneider is an expert here, I guess. And finally, if you're working with E being just a finite extension of FP, well, then we rather use notation pi And in that case, it is the smooth admissible representation of GL2 QP over E. So I'll come back to this. Well, smooth, I guess you all know what it means. It means the action of the group is locally constant. I'll come back to what admissible means in this talk. Yeah. And so there's a way to go from B to from characteristic 0 to characteristic P. It is reduction mod P. So by reduction mod P, you can take an open ball, an open unit ball in your Banach space, and answer it by FP bar. Well, yeah, so I have to, and you get something which is smooth admissible. So in some sense, in this work, starting from rho, the truly important representation is really B, and from B you get some kind of derived product, which are B an and B naught tensor FP bar. You may have to semi-simplify here. It may depend on which lattice you take. Anyway, so this is a Banach space. This is not anymore a Banach space. This is a locally analytic representation, and this is smooth representation of GL2 QP. All this is now essentially completely understood for GL2 QP. And so the aim that some people have would be to try to generalize this. So during this talk, I will recall to you instances of all this stuff for QP, and then for so in the introduction, I remain kind of not so precise. So the aim is try to generalize this, to extend this to GL2F. Well, I mean, you can also try to extend it to other groups, but GL2F is a kind of natural next step. And so at the beginning, people, so including me and others, started to think about this. We were quite optimistic. I mean, we were reasonably optimistic, and what turned out to happen is that this is much more difficult than for GL2 QP. As you will see, I guess in the talks, this is not. It's not, in some sense, it's not even really comparable. Yeah. So yes, the aim we would like to, starting from a continuous two-dimensional representation of Galois QP bar over F, where F is a finite extension of QP. To GL2F, sorry, where F, of course, where F QP is strictly is a finite extension of QP, and of course we have in mind the case F different from QP. And there's a problem if you want to do this. I mean, so far, that it appears to be much more difficult than for F equals QP. So this surprised very much people, because usually when you have something working for modular forms, for instance, you have, apart from technical problems, you usually have also results for Hilbert modular forms over totally real fields, which is kind of the global analog of this local stuff. But here, you really have serious differences between the two cases. And there were one category of people who maybe have realized this, although not in the setting of this program. Those people working with Hilbert, overconvergent Hilbert modular forms, they were stuck on certain problems for years, such as Coleman classicity or building a Maser Coleman eigencurve and so on. So all this, you will find it back in this setting. So it's not a surprise for these people, at least. But you will find it, you'll also find lots of other questions, unfortunately. So what I'm going to...
Even if it's an unramified?
Yes, even if it's an unramified. Well, you know a little bit more, but... so, I mean, as far as I'm aware, in no cases we have an analog of B. So we start from rho, representation of Galois QP bar over F, to GL2E, say E QP being a finite extension, or even, I mean, we usually take it so that it contains the Galois closure of F. Okay. Well, as far as I know, so far we don't know B in any case. We have Banach spaces and so on, but we have, it's not clear. it's not clear what to do to get a B. We're not even sure there are not several B's and so on, as you will see. So I'm not going to talk about Banach space anymore in the almost not anymore in the remaining of these talks, but I'll talk about the derived products we got from B. So there were of two kinds, if you remember, the locally analytic vectors. It's kind of easier to work with these. It's less rigid, so although I mean, not in a math sense. It's more flexible. You can do more things. It's easier in some sense, even though you don't have a norm, so you cannot reduce this mod p. And there's the other derived product is, let me just denote it B bar, which is take an open ball and reduce mod p and maybe semi-simplify. I mean, it might depend on the open ball. Let me remain vague here. So here this is over QP, but here this is this time over FP bar. So these things you can try to see what's going on for these things, which are kind of easier, and this is what I'm going to do in this talk. So the first two talks I will speak about such things like B bar, although there won't be any B, okay? And the last two talks I'll talk about B-adic, without knowing what B is. And you will see that in both cases we have there's still the main bulk of what probably one day will be the main part is still to do. So what has been done is just some kind of a very partial result. So only partial results so far. I'm trying to give a survey of those partial results, at least those that I am aware of. Only partial results so far.
Did you say B bar involves semi-simplification?
Yeah, no, because when you reduce a Galois representation mod P, you may have extensions in one sense or in the other sense. It depends on lattice. Well, you get the same thing on the Banach space, so that's why. But I won't have any B, so I will just focus on the characteristic P situation. Okay, so let me just write. Okay, this is not canonically defined from a B. This is all that I mean. Okay.
B is irreducible?
Sorry?
If B is irreducible, is it? If B is irreducible.
Yeah, well, if you have a, well, certainly it can happen that it is canonically defined, but not in, well, maybe anyway, I won't talk with any B's. There won't be any B in this talk just after now. So, okay. So from now on, that's the contents of the first two talks. I will assume that E is a finite extension of FP. And well, I can, in that setting, I can tell you the main two reasons why it's so harder. And then we'll see more precise statements in the rest of the talk. But the main two reasons why it's so much harder, even mod P, are the following two reasons. The first thing, that there are many more. It turns out that there are many more. So smooth, admissible. You can even add irreducible if you like. That's not the problem. Even irreducible representations of GL2F over E than representation of GL2QP over E. Sorry, in this case, I will assume for the two talks, I will assume moreover that F is unramified. Not in the characteristic zero talks after, but for these I need F unramified. So that, I mean, the work that I'm going to talk about has not been generalized to the case F ramified yet. Okay, so there are many more representations, but many more, it's a kind of a, there's so many you don't know what to do. And the more, historically what happened is we find more, and as time passed by, many more coming in constantly. So the situation now is that we have too many representations on the GL2F side. In particular, there's no hope of any kind of naive correspondence, since on the Galois side, you have the same number of representations basically. So you have no more correspondence from a purely local naive point of view.
Sorry, same number meaning for QP and F, is that what you were saying? On the Galois side when you say
Yeah. Well, I mean, you don't have any
Qualitative jump.
yeah, qualitative jump from the Galois side, whereas you have something, a jump on the GL2F side. And the second reason, which is, see, each of these representations is much harder to study. So not only you have plenty of them, but each of them is a nightmare. Each of, I mean, as far as I am trying to do things with these representations, each of these representations, well, almost each of these, I mean, you have principal series which are easy to deal with, but most of them are not principal series. So each of these representations turns out to be very hard to describe explicitly. Very hard to describe explicitly. And we have no explicit equation so far, even after a certain number of people including me, try to work on this. No explicit equation so far. We have equations, but it doesn't give admissible or irreducible representations. It gives things which are still of infinite length and so on. You will see. No explicit equations so far. Whereas for QP, we have trivial explicit equations right away. Okay. So what I will do in this first talk is starting from a row, which is a representation of Galois QP bar over F to GL2 of E, I will associate something which is presumably something which is, has vocation to disappear one day, or at least to be refined. I will describe a way to associate to rho an infinite set, but it will be infinite, assuming F is different from QP, which I am tacitly assuming, an infinite set of smooth, admissible representation phi of GL2F. So this is my aim in this first talk. This infinite set is very badly understood, but it is still very small with respect to all possibilities you can have. So this is I mean, it's still very specific from the point of view of the local theory, although it remains infinite. And in the second talk, I will show a way how to refine this set by defining a subset, which will still be infinite, but this way we use phi gamma modules. This is a little bit strange, but there's a way to refine the set, but it's still infinite, unfortunately. And I don't know up to now any other way to refine again. So that's the first talk. And second talk, next talk, can refine this set, meaning we can define a natural subset, which in the case of f equals qp will be only one representation and will be exactly the correspondence for qp, but in the case as soon as f is different from qp will still be an infinite set. The set using phi gamma modules. So the idea of using phi gamma modules was found for GL2QP by Colmez. Of course, it's natural to see what's going to happen. And of course, as you may expect after some experience, here also you have a jump. I mean, something is not going on as you would have liked it to be. Okay. Okay, so now let me start with just reminding you quickly the mod P correspondent for GL2QP, where everything is fine. So I need a little bit of piece of general notations. So G will be GL2F. Nesto K will be GL2 of OF. OF being the integers of F. F is unramified in the first two talks. Well, I already said it. And I will assume that the residue field of the E of the coefficient is contains the residue field of F. So I assume that the cardinality of Hom OF mod P in E is a finite extension of QP is the same thing as the degree of F over QP. F being unramified, this is the same thing as the degree of the residue field. Okay, so let me now recall a little bit of a standard kind of standard notations and representations one can play with in this setting. So if sigma is a finite dimensional representation of K F cross, the unit in F, over E, I will denote the by the following notation, and Kf cross to G of sigma, the compact induction. So the compact induction, very quickly, for those of you who don't know this is a space of functions on G which have compact support modulo Kf cross. Functions from G to the underlying space of sigma, and which behave in the which satisfies f of kg. Kg is sigma of k applied to f of g if k belongs to k f cross. Okay.
Remark here about the homomorphism, the order of the homomorphism.
Yes. Field homomorphism.
So
Yeah.
that's E, the finite extension of F.
Yeah. E contains the residue field of f. Yeah.
So the homomorphisms over, I see, over that.
Okay, so this kind of compact induction appears naturally in that setting, and it satisfies the following property. Satisfies the property that if you, the endomorphism has G, the G equivalent endomorphism of this induction is just generated by, as a polynomial by one endomorphism, which is traditionally denoted by T. So T is TP in some sense. So let me just give you the example of sigma being trivial, if you want to have a vague hint of what T is. If sigma is trivial, then this compact induction is just functions on the vertices of the Breuil-Attitz tree, and T is the map that with compact support, yeah, with finite support, absolutely. And T is the map, but that is the map that maps a function to the functions, which is the sum, which to a vertex associates the sum of the value of your f on the adjacent vertices. Okay. Well, if you know what the Breuil-Attitz tree is, you have a vertex, and around you have as many vertices as the cardinality of the residue field. Okay, and you define a new function. The new value of this vertex is the sum of the values of the adjacent vertices. Okay, so this is T. It is equivalent and so on, and this generalizes when sigma is different from 1. Okay, let me just say that. So what is the mod P correspondence now in terms of compact induction? It is the following. So you can refine it using phi gamma modules, but I'll talk about this in my next talk. So let me just state it as directly as possible, and assuming my Galois representation is generic, because otherwise you have some special cases that perfectly understood now, but that are not understood for f different from qp. So let me, in the case rho is reducible, then you can write rho as an extension up to twist. So up to twist. But twist is not a problem because you twist also on the GL2 qp side. Then you can write it as follows. Omega r0 plus 1 unramified of lambda star 0 unramified of lambda minus 1, where omega is cyclotomic character mod p. R0, well, R0 is an integer. I have to assume for what I'm going to say right away that it is bounded by, it is between 1 and p minus 4, which means that I miss cases, but these cases require specific treatment. This is kind of, which I don't want to go into. But for GL2QP, everything is understood. Okay, let me, so this is what I call here the generic case. which will be the case I will deal with for f different from QP anyway. And unramified of lambda is the map which sends the geometric Frobenius to lambda, geometric Frobenius on the Galois side to lambda. It's an unramified character. So what is pi? Pi being a smooth admissible representation of GL2 QP over FP bar in that case.
So is this your assumption on rho?
Lambda is in E cross.
This is what you're assuming about the Galois representation?
Yeah, up to twist, it's always like this. Well, except that not necessarily with these bounds, but I tell you that if R0 is equal to 0, equal to P minus 3, and so on, you need a more specific treatment that I don't want to go into.
Right, no, I understand. But my question was, you're assuming this about rho? Or
No, I'm not. Up to twist, it's always like this.
any continuous representation?
Yes, yeah, over FP bar, yes.
Ah, I see.
Up to twist. Okay, so, well, then if you don't want to assume that it's just twist and twist again on the GL2 QP side. So what is pi? Pi is the unique, so split if star equals 0 and non-split if star is different from 0 extension of the following kind. So it's an extension between two representations which will be irreducible in this generic case, which will be two principal series, but I write them as compact induction. So it is exactly the following. Sim R0 of E square modulo T minus lambda. This is a subobject, unique irreducible, irreducible subobject as a sub, yeah, and then and sim P minus 3 minus R0 I square mod T minus lambda minus 1 tensor omega R0 plus 1 composed with the determinants. So these turned out to be principal series. So pi is a unique such extension which is split if it is split on the Galois side and non-split if it is non-split on the Galois side, which means that you have to prove that there is indeed a unique non-split such extensions on the GL2 QP side. But this it is known. And these two representations are principal series, and you can rewrite them in a more in a nicer way, where it's easier to remember, as parabolic induction. So this is easy. This is isomorphic to the parabolic induction of from the upper parabolic to G of the following characters of the torus that you inflate to the Borel, and ramified of lambda minus 1 tensor omega R0 unramified of lambda. That's for the sub 1, and this one is and from the Borel to G of omega R0 plus 1 unramified of lambda tensor omega minus 1 unramified of lambda minus 1. So this tensor product of two characters means I just take this is viewed as a character of this entry. This character is a character of this entry, and I just take the product. And I induce by taking functions from G to E, which such that f of bg is this character of B times f of G, where B is in the Borel circle. Usual induction. So so this is a general fact that we will meet again in the four talks. That if we have rho, which is isomorphic to something like this, chi1 omega star 0 chi2, then we have two principal series which comes in and which will play a role, which are, this is exactly what is going on here. This is chi2 tensor chi1, and the other one will be n chi1 omega minus 1 tensor, chi2 omega minus 1. So these are principal series. It's called principal series. And they will appear, even for GL2F, they appear. So that's why I insist on them. For GL2QP, you have essentially nothing more except that you have either a direct sum of these two, if it is split on the Galois side, or a unique extension between these two, if it is non-split on the Galois side.
The assumption F is equal to QP is in force since when?
Yeah, he is a... Yeah, you're right.
It's nowhere written.
Yeah, it's nowhere written, and you're right, this is important. So F equals QP. I just give you the QP case, and then I switch to F different QP right away, right after.
Sorry, also, could you read that thing in the quotient? I can't quite. There's omega to the R naught plus 1. What?
Composed with determinant.
Oh, I see.
Because omega is a Galois character. So you have to, use a local classification theory and so on.
And there's sim of P minus 3 minus R naught.
P minus 3 minus R naught, yes. Yeah, R naught is smaller than P minus 4, so I have no problem with.
Sorry, is rho equal to pi?
No, rho is a Galois representation. And pi is a GL2QP representation. Rho is two-dimensional, pi is infinite dimensional.
And did you already tell us what admissible representations are?
I will, in a minute. Okay, so let me now remind you or tell you the irreducible case. And then I switch to F different from QP.
I'm sorry, maybe
Yes.
just interrupt on that.
So rho
When you said
irreducible.
for QP, you said this is the unique.
Unique, no, yeah, either split if rho is split,
Right.
or non-split if rho is non-split. Well, there's a unique non-split extensions between such two principal series.
In some category of admissible representation.
Yeah. Well, I mean, if you have such an extension, it's automatically admissible if those the two
I see.
are. But no, it's a unique such extensions.
But so it would occur in some category of smooth representations then, or something?
Yeah, it's a smooth representation. Yeah, well.
No, unique. I'm just trying to understand.
In the category of smooth representations, you're right, there's a unique non-split such extension between such two principal series, which is something you have to prove. But okay, so now I switch to rho irreducible. In that case, it's somehow simpler to state. So, which means that up to twist, again, you can always write rho as follows. Rho restricted to inertia is isomorphic to omega 2 R0 plus 1, 0, 0, omega 2p R0 plus 1. Where R0 is, again, I have a genericity hypothesis that I can work out the non-generic case, again, without problems, but, and omega 2 is Serre's fundamental character of level 2. So character of level 2. And then what is, so yeah. And I have to assume the determinant of rho, otherwise, is the cyclotomy character to the R0 plus 1. So up to twist, I can always assume that rho is like this. And what is pi? And pi is simpler. It's the following quotient. You just induce sim R0 of E square, and you mod out this time just by T. And this turns out to be irreducible, admissible. Yeah, I've not told you what admissible means, so I'll tell you in a minute. So this is what goes on for GL2QP. Okay, and so now you can, you can play with these representations a lot. You can compute their invariant under whatever compact open subgroup you like. You can compute their restriction to GL2ZP, see how it looks like, and so on. And when you compute, for instance, their restriction to GL2ZP, you find out the following property, which will turn out to be important for the stock, that you can understand the GL2ZP circle of these representations. And it's a nice way. So let me state this, and then I switch to GL2F. So one more property is that one has, so recall that the circle is the maximal semi-simple sub-representation. And the circle as a GL2ZP representation of this pi turns out to be finite dimensional, and it is exactly the following kind if it is sim R0 if star is different from 0 and rho reducible. It is sim R0 direct sum sim P minus 3 minus R0 tensor omega R0 plus 1 if star equals 0 and rho reducible. So this is the other, these are two weights, the two representation of GL2 ZP that appear in the two principal series, if you look. And sim R0 plus sim P minus 1 minus R0 tensor det R0 if rho is irreducible. Yeah, so that's something very different if you have any, if you know a little bit about the smooth theory in characteristic 0, the theory of the classical local Langlands correspondence. When you reduce a representation of pi to a compact open subgroup, it is a direct sum of infinitely many representations of finite dimensions, because the theory of representation of compact open subgroups in characteristic 0 is semi-simple. It's just as for finite groups. Here, it's not at all the case. You have many, many extensions, and in particular, the circle, meaning the maximal semi-simple subrepresentation is finite dimensional, which means since the representation itself is infinite dimensional, all the rest is in extensions. So this is a major difference with the smooth characteristic 0 theory. You have to, in one case, you have infinitely many direct summands, and here you just have two long series of extensions. I mean, if you want to have a vague idea. And the circle, there's these representations, which are called weights, which are called Serre weights, which is irreducible representation of K over E. This is what is a Serre weight. These Serre weights associated to the given row already had appeared in the arithmetic, in studying congruence of modular forms, basically, I think, due to several people maybe, but mainly to Chandrasekhar, I guess. And so this is something you can sum up as the soc of pi is the direct sum of sigma, for sigma being the Serre weights of rho. This is what you find a posteriori for those for this mod P correspondence. Okay, so now that's all for QP. Now I'm
sorry.
Yes.
What does that mean? That is sum of sigma for what? When you say sigma for
the sigma being the Serre weights of rho. So the Serre weights of rho, by definition, are these two things in that case. And okay. So let me come to F different from QP now, where I speak about these Serre weights.
Sorry, there's one other question.
Yes.
But in the characteristic 0 case,
yes.
When you look at the K representations, does any given representation appear with finite multiplicity? Or?
Oh no. They.
Is that right?
Of course, that's the admissibility.
No, but I mean as subquotients. No, what do you mean by multiplicity? You mean as a? No, one representation occurs. It's periodical if you compute the restriction to GL2 ZP. So one representation will occur infinitely many.
0, you asked.
Yeah, in the complex over in the Archimedean.
Yeah. So yeah, it's admissible. This is what Peter says. So it's fine. Yeah, of course.
Multiplicities are fine.
Okay. So what does admissible mean in that context? Once and for all, you might forget. So it means that pi under any invariant, the invariant of pi under any open compact subgroup is finite dimensional, has finite dimension. This is by definition pi admissible in all characteristics. Okay, which doesn't contradict this because. Okay, so now I switch to 2. So recently there's been work. There's been work by Buzzard, Diamond, and Jarvis. They have formulated a generalization, have generalized Serre's conjecture, which I'm not going to talk about, even though you might think this is more interesting. You're right, but. And in formulating a generalization of Serre's conjecture, what they have generalized is the set of Serre weights for a given row. So they have defined. They start from a row, which is so this time it's F different from QP, okay? and F unramified. So starting from a row, two-dimensional representation of Galois QP bar over F over FP bar, they define a set D of rho, which is a finite set of cell weights, meaning of irreducible representations of K over E, K being GL2 OF. So I'll give you, at the end of the talk, if I have time, I'll give you an example of this. But this includes some kind of combinatorics, so which is a little bit not so nice to, I mean, a bit technical to explain. So anyway, this property here suggests that whatever we want to find on the GL2F side, whatever representation pi of GL2F we would like to have on the GL2F side, we expect it to satisfy the following property, that its circle is the direct sum of the sigma for sigma in this set of weights. But now the set of weights is much larger. It has a big cardinality. So in the if rho is generic, if rho is generic enough, so if rho is sufficiently generic, which just is what I assumed previously, then the cardinality of this D of rho is always a power of 2, is 2 to the D, where D is an integer between 0 and the degree of F over QP. And it is exactly, and D is exactly F, the degree of F over QP, or the degree of the residue field, if and only if rho is semi-simple. Rho is semi-simple, meaning either irreducible or split extension. Semi-simple. So just to tell you that there are many more weights. Okay, it's a power of 2. So it's growing with a degree, it's growing exponentially, not linearly, and so on. So if you look for a representation, so you have many weights. Of course, this fits with what we have here. This is 2 to the 0, and this is 2 to the 1, and 2 to the 1 in the semi-simple case. Okay, so we'd like to build on what has been done for GL2QP and try to define some pi, being representation of GL2F for a given rho. And you find the following main obstruction as soon as you start somehow. So you start from a row like this. You can still, up to twist, write any row like this. Stay in the assuming rho is reducible to start with. And then you can perfectly define your two principal series exactly in a similar way. And so when I thought about this already some time ago, trying to go from QP to F, one of the very first completely naive hope I had, but without checking, was the following. What's different when going from QP to F on the Galois side? You have more extensions. The space of extensions basically has a dimension, basically the degree of the field in any case. So, well, what do you expect on the GL2F side? You expect that you will have more extensions between these two principal series. And so you have a nice correspondence. So this is what I had as naive hope. And then you compute and you find there's no extensions. As soon as F different from QP, no extension as previously. No extension, no non-split extension between these two principal series. Okay? So you have the feeling that you miss something in the middle when you compute. That's the problem for a rho being reducible. Okay? So the naive thing you may have hoped, the corresponding extension on the Galois side to extension to the GL2F side, is not what is happening. And now you assume rho irreducible. So this is for rho reducible. So yeah. Now rho irreducible. And well, then you say, okay, maybe we can consider something like this, and sigma mod t, for sigma being, say, in the set of cell weights associated to rho by Perzert, Diamond, and Jarvis. And then you realize this is of infinite length, as infinite length. So for QP, you had only one extension, and for QP, this was irreducible admissible. So you see the two things break down. So you have to You have to find something else. And it's even worse than you can think of. As far as I know, even today, no one knows how to construct explicitly irreducible admissible quotient of these representations. We know some abstractly that some exist, but we don't have explicit equations. So let me say this. Still an open question. So far, not known how to define explicitly, meaning with explicit equations, finite number of equations, irreducible, or even finite length, admissible quotients of this representation. And sigma mod t.
So this is for every zero weight that you get to continue?
Yeah. For every weight. I mean, no, you can just consider this for any weight now. You have the same problem for any weight. This is not. I mean, this is independent of the.
This fact that every extension splits. Can you say briefly why?
Sorry.
You said that there are no non-split.
No.
extensions.
Yeah. Well, when you compute, do you want the reason why?
No, I mean that's no detail. But
I guess I've forgotten to tell you. When you compute, let me see. No, I mean I have to think. I didn't look at this for a long time now. I mean, but I have.
What will be the difference from QP? That's the odd.
No, I have to. I don't have it in mind. Let me. No, I mean well, I'll tell you. I have stuff here, but I can't tell you right now why the reason. Forgotten. Okay, so we will kind of proceed indirectly and only have partial results, as I told you already. So I can tell you I spend a lot of time on this, but I'm not the only one, so there's not a reason why. So well, I have a student, Chinese student, who computes a lot. Just again couldn't find such explicit quotients, and also there's I guess other people who tried. Michael Schein, I guess, tried also. But, so it's very hard to compute explicitly as far as you're not anymore with QP, because with QP you are computing essentially with a line. All extensions of, I mean, but as soon as you're not with QP, the dimension grows. Well, the dimension of the. Well, anyway, it's very hard to compute explicitly. Okay, so we will proceed indirectly to construct abstractly representations that I think are at least contain what I hope one day will be the right representations. Okay, so we'll proceed indirectly. So I need some other notations now. We denote by I inside K. This is the subgroup. This is the Iwari subgroup. This is a subgroup of matrices which are congruent, which are upper triangular modulo P. Okay, this is also called the Iwari subgroup. Yeah, and I will denote by I1 input into I the subgroup of the subgroup of matrices. Yeah, which are congruent, which are unipotent mod P. This is called the pro-P or Iwari. This is the pro-P subgroup of I. And finally, I need another group which is not compact. This is the normalizer of the Iwari, but this is a subgroup of G generated by I, F cross, and the matrix 0, 1, P, 0. Okay, inside G. Okay, I need the. So let me introduce a certain representation. So I will denote by d naught of rho So again, what I'm going to do actually comes from what we saw further a refined examination of the GL2QP situation. You can go further than just looking at the circle. You can do the following. I will denote by d naught of rho to be the maximal for inclusion representation of K over E such that it satisfies the following properties. So the identity plus pk act trivial, so that it is a representation of GL2 of the residue field. Second, the circle the circle of the scale representation is what we want to be, namely the direct sum of sigma for sigma in d of rho, the set of weights that I've not made explicit. I hope to make explicit in some of my talks. And finally, I want the extra properties that sigma in d of rho only appears as in the circle. Only appears in the circle. So not in the middle, not as a subquotient. So one can prove that such a representation exists. This is a simple and nice exercise of representation theory, and it's not specific to d of rho. It exists for any set of distinct cell weights, independently of any rho. Okay, so, and this representation has some nice properties, which I'm just going to go right to the point, so I'm running out of time. That you can compute d naught of rho, the invariant under the pro p way. So this is always different from 0, and this is always different from 0 because I1 is pro p, and we are in characteristic p. So you know this. You always have invariance, and we are E fp. E is over fp. So this is always different from 0.
The last condition doesn't mean any subquotient is a sub? Is that what?
No. It means that the subquotients are not in D over. They're other cell weights.
Yeah, that's what I mean. The only subquotient that's in the circle. I mean, that's isomorphic to something in the circle is in the circle.
Yeah.
Okay.
Okay. So this is always different from 0, and you can prove that you can always endow this with an action of n. One can always endow d naught of rho I of 1 with an action of n compatibly with the action of I we already have, compatibly with the action of I. And in fact, there are infinitely many such actions of n. In the following sense, you view, well, d naught of rho I1, you see it into d naught of rho, and then so that you kind of rigidify it by saying in d naught of rho, and then you try to put an action of n on the I1 invariants, and so you have scalars everywhere, and so in general you have infinitely many such actions as soon as you see this inside d naught of rho. So let me give you an example with GL2QP, and I guess you understand. So assume rho is split, and f equals QP, which of course is not the thing I want to be, but I want to explain here. And then you can compute this d naught of rho is the following representation. So you have your two weights in the circle, which we've already seen, plus sim p minus 3 minus r0 up to twist. So there's a twist. Let me forget about the twist here. How is it determined? And the naught of rho is a direct sum of two extensions. So here, this is a unique extensions with p minus 1 minus r naught, and there's a twist. Don't forget. And there's a unique such extension as a GL2FP representation between these two cell weights. And here it is sim r0 plus 2, and there's a twist again, which I kind of forget. And there's a unique extension between these two cell weights, unique extension which is a representation of GL2 FP. And d naught of rho is the direct sum of these two extensions. Okay? And when you compute d naught of rho I of 1, it has dimension 4. It is sim R naught I of 1. So it's the I1 invariant of this direct summand, the I1 invariant of the other direct summand. Okay? So you have, of course, the I1 invariance of each sub-representation because any cell weight has a I1 invariance because of this property, and this I1 invariant has dimension 1 particular. But you have a canonical lift of the quotient also, of the I1 invariant of the quotient. Canonical, this is due to the structure of the extension. This is a small principal series, if you know this. Canonical lift of sim p minus 1 minus R0 I1. Plus the same thing with the other extension.
Sorry, you said all these invariants are dimension 1?
This is dimension 1, this is dimension 1, and this is dimension 2. So in the all, this is dimension 4. And so what is the action of n you can put on this? Well, you don't have choice. You have to send this I1 invariant to this one. And likewise here. And you see when you do this, so you choose a basis for this. Choose a basis for this. And you choose this vector to a scalar times this vector. But you have a scalar. So you can tell me, OK, but we can scale. You can scale here, but of course you cannot scale anymore in the extension. So this is what I mean by the fact that you may have infinitely many actions of n. OK, so you can do this for any f.
Sorry, n was a subgroup generated by I1 and...
This is normalizer of the Iwari. It is, maybe I've erased it. It is normalizer of the Iwari. But basically, the most important thing is the action of this matrix. You have to look at the action of this matrix. OK, so you can do this in general. And you can prove the following theorem, which is, well, so far it cannot do much better, unfortunately. So theorem 1, which was a theorem I proved some time ago with Vitotas Pascunas. Okay, is the following: for any action of n on d naught of rho I1, there exists a smooth, admissible representation pi of GL2F over E such that it satisfies the following condition. Well, it contains the naught of rho in a k equivalent way, of course. It contains d naught of rho I of 1 invariant under I1 in an n equivalent way. The circle of pi as a k representation is what we want it to be, namely the direct sum of the sigma for sigma in the set of cell weights defined by Buzzer, Diamond, and Jarvis, which is a big set, as soon as f is different from QP. And you want pi as small as possible, so you can take it generated by d naught of rho. So, I mean, let me rephrase this in a different ways. If you want to build pi satisfying only this property, which is the guide we had for going from f to from QP to f, there are many such pi. By taking this representation d naught of rho and asking that pi contains d naught of rho and contains one of the possible actions of n, you kind of restrict yourself to certain specific representations satisfying this property on the circle. They are very specific. Okay, so we have reasons to believe, computational reasons not to believe that this, what appears on cohomology, will indeed contain this d naught of rho. Okay, and now I'm going to make a series of remarks on this theorem. So let me just say that the proof is abstract. The proof is abstract, and it's based on an idea which is not due to me, which is based on an idea due to Pascunas, based on the idea of using injective envelopes. makes use of injective envelopes. This is why it is so abstract. It is just an existence theorem. Abstract existence theorem makes use of injective envelopes. Okay, I don't have time to say more on this proof, but I have time to say important remarks and addenda to this result.
Oh, sorry, before you make the important
Yes.
remark, you said that you have reason to believe that,
Sorry?
that the representations that appear in comma value contain the not of row.
Well, we have a little bit of evidence of such yeah.
So you have some comma value for construction of
Yeah, you can take whatever Shimura curve you like, or you can take something with quaternion algebra. You can even, and look at the inductive limit over the compact open subgroup at P, cohomology, mod P, so on. Well, any cohomology group where you have an action of GL2F over F P bar. So let me make a series of important remarks on this result. Try to understand. So first, so this is the bad news. If F is different from QP. So you see, when we worked with this with Pascunas, we had the feeling that if we give ourselves the circle, this is not enough. There are plenty of such representation pi satisfying this property. So we're going to kind of look at more specific pi, and we construct this d naught of rho. And there are plenty of actions of n on each of d naught of rho I1, but for each action of n, you have such a pi, and we were hoping that this would be enough to determine completely a pi. This is not the case. So I have a student who has proven that there are infinitely many such pi for each given action of n, and there are already infinitely many given action of n for one given d naught of rho. So you have to go beyond, you have to go further. This is still not enough. You always have, at least to determine a unique pi. But of course this is okay, well, if f equals qp, there is only one pi. Pi for each action of n. For instance, in the example that is above, I told you that you had several actions of n because you had scalars. Well, these scalars are related to the unramified characters in your parabolic inductions, actually. Okay, so that's and I have not specified them here. So each time I specify an action of n, I specify the unramified characters that are, the unramified part of my characters. And well, for such, once I specify n, there's only one such pi, and it is the extension, the unique extension I've given to you at the beginning of the talk, in case it is non-split, and if it is split, it is a direct sum of the two principal series.
Oh, sorry, so you said in this case, in the f equals qp case, the n action is also determined by the
No. You've got several n actions, but once you fix one, you've got only one pi satisfying this property.
Right, but you do have a correspondence for f equals qp.
Yes, because this only depends on rho restricted to inertia. I've not made use of the full.
Oh, I see what you mean.
So if you plug in the unramified characters, which is exactly the action of n, then you get only one pi.
Yeah, that was my question.
Yes. Okay. Now go on. But still, we have two non-isomorphic actions of n give rise to disjoint. Well, this was implicit in the way I stated the theorem, but give rise to disjoint sets of pi. So if you fix one action of n, then you have infinitely many such pi by the result of this student, but there are nothing in common. All the representations are different. And of course, we have no explicit equation so far for any of these pi. Well, at least if you avoid the case, for f different from qp. Okay. So one temporarily, in the situation as it is now, starting from rho, I associate the set of pi for as in the theorem, for all possible actions of n, as in theorem. So thanks to your remark, this is not exactly the mod P correspondence because I've not used, in the case it is reducible, the unramified characters involved in row. This is exactly what you said. But I explain in the next talk a way to refine the set for all f, which will exactly, in the reducible case, exactly include this refinement and give you the correspondence mod P. But it will still be infinite when f is different from Qp for all actions of n. So this is temporary. Okay, and let me state the second theorem, if you allow me 2 minutes again. Because we can say a little bit more on this representation about their properties of being irreducible and so on, and about what we could expect very quickly, and then I'll stop my talk. In the at least in the reducible case, what could replace this fact that there's no extension between these two principal series we had? So the following theorem 2, which is again with Vitas, Pascunas. So I state it, if rho is irreducible, then any pi, as in theorem 1, is irreducible for any action of n. And so it's you see, it's still irreducible admissible representations, so, and still so many. So this is not a problem of being irreducible or not. And if rho is reducible, any pi, as in theorem 1, is reducible. And we can say a little bit more. In that case, we don't know that it is of finite length. We just know it is reducible. And when we know it is reducible, because we know that it contains always the principal series that is in sub-object. So this is easy to prove. If you have rho that is isomorphic to chi1, omega star 0, chi2, then can prove that any pi that you can associate to rho, and even if you have infinitely many, with don't know how to, we don't understand them, but we know something. We know they all contain, any pi contains the first parabolic induction, which was chi2 tensor chi1. And of course, it's not just this. So this is why it is reducible. It contains this. Okay, so, and if it is split, if rho is, yes?
Didn't you have to mod out by some...
Sorry?
Wasn't there modding out by some key action or something?
No, this is parabolic.
Oh, that's not the compact induction.
Yeah, well, it is a quotient of a compact induction, but also to G. But it's easier to, because you see the two characters here, you see them here. You can rewrite it also as a compact induction exactly in the same way. For principal series, you don't have any jump on the GL2F side, but that's the only case. And when rho is split, if star is 0, so remember in the GL2QP case, you had the two principal series which were there. Well, here it's the same. Both are here as sub-object also, but you have some other stuff that you don't understand. If star equals 0, both principal series, both and chi2 tensor chi1 and chi1 omega tensor chi2 omega minus 1 are sub-object for any of the pi, but you have, this is far from giving you your pi. Okay, so what do we hope very quickly to finish with, and then just 1 minute and then I stop. So one can prove that in the case rho is split, we don't know, I mean, it's too complicated so far to understand all these pi, and maybe not all of them are interesting. I mean, this theorem gives you, it's highly probable that this theorem gives you, this one gives you too many pi, but some of them have the following structure. If rho is split, some pi are like this. So you have these two principal series. Let me call it pi naught. So let me call this one pi naught. And let me call this one pi f, where f is the degree of f over qp. So you have this pi naught, as a subobject, you have this pi f as a subobject, and in the middle, you have exactly f minus 1 irreducible admissible representation of GL2F that are not principal series. That depends on your order, Buzzard, Diamond, Jarvis weights, and so on. So you can prove that some of these pi are like this. Okay. But not all of them. Who has proven that there are pi in this theorem that contain these two principal series, but are not direct sums like this, with these guys being irreducible, all irreducible, admissible, and not principal series. They're called super singular in the terminology, or supercuspidal. But anyway, I have reasons to believe that these are the one we should concentrate on. Of course, we don't understand this P1, Pi2, and so on. Okay, they also depend on hidden choices that we don't. And in the case where it is non-split, when rho is non-split, so we have no instance here, I mean, of any kind of any pi for which we know it is of finite length. But I would hope one day that we can the good pi may look like this. So you have this principal series to start with, okay, and then you have in the row all these representation that I've not specified to you, but you can specify the circle, at least the K circle, and so on. And you end up with the last principal series. So you see this would kind of compensate the fact that, so this means an extension, non-split extension, which may depend on some data. So, it also might be the case that if you want a non-split extension between pi1 and pi naught, you need you don't have this for all pi1. Anyway, this would compensate the fact that you don't have extensions between pi naught and pi f when f is different from qp, okay, because you have something in the middle. So yeah, so next time, as I told you, I will refine the set by plugging in what Kolmes did for GL2QP, namely phi gamma modules over f, and we'll see that there's some seems to be some link with a tensor induction on the Galois side, at least from a certain point of view. So